Okay, so how do we draw these cyclical stuff? Again, we're going to practice this a lot now. Okay. Okay. So again, make sure you're writing this because we're going to be using this a lot for the next like maybe 30 minutes. So drawing the ring version of aldose and ketos. So one is number your carbons starting from the end closest to ketone or aldehyde. You're like, isn't it just a rank? Why would I number it this way? I want to number it from the other way. So when it comes to carbohydrates, you have to there's a standard numbering. Later we're going to talk about like how these carbohydrates are attached to each other. We say, yeah, so carbon 1 attack carbon 4. So there's a standard way of numbering it. So if you number it properly right now, it becomes a habit for you. Again, even though this is not necessarily connected to that topic, but it becomes a habit. So when you see that, that's just like, okay, sure, I get it. So yeah, so we pretty much number, again, I'm going to do an example just for you to see this. 2 based on the expected length of your ring. I'm going to explain. Find the OH that attacks the aldehyde. So because again, remember like when we were talking about like in previous chapter, it's like one of these like OHs have to attack either this ketone, this aldehyde or ketone to create a cyclical structure. That's like how we got the hemiketal or hemiacetal, right? But then you're like, what do you mean by the expected length? Because again, we're going to talk about this. There's 2 different types of rings you can get. Yeah. So because we can get 6 atom ring or 5 atom ring. I'm not saying 6 carbon or 5 carbon. 6 atom ring or 5 carbon ring. So 3. So aldehyde or ketone will turn when you attack it into hemiketal or hemiacetal. 4, that carbon, the carbon of hemiacetal or hemiketal will be your anomeric carbon. This is a very important carbon. A lot of things are based on this. But again, you know, like how when you draw a ring, I say it's a ring, you can't place it on the right side or left side. of that like group that you're attacking with. Unless they change it this year. By convention, the anomeric carbon is clockwise to the oxygen on the rank. 6, it will be the anomeric carbon. This is also very important for those later. It will be carbon 1, because again, remember, like we said, there's a standard numbering process for aldose and carbon 2 on ketose. And 7, number the rest of carbons on the ring. Eight, again, this is like a reference, remember? I'm going to show you how all of this applies. When you're trying to put things on the so this is like, you have to just understand what I'm saying here. CH2OH, let's say OH and hydrogen. So everything, because again, when you get a ring, you have a lot of these like OH stuff, right? You have to wonder like, okay, are you gonna put it on the axial or equatorial? Not axial, equatorial, like up or down, or wedges and dashes. So, well, I mean, we're gonna be drawing chairs, so up or downs. Generally speaking, anything that is on the right side is actually down. Anything on the left side would be up. It's like an airplane that is turning right. So everything on the right side would be down. Anything on the left side would be pointing up. So if you have CH2OH at the end that is not on left or right, you rotate the carbon so the attacking OH will be pointing down and CH2OH will be either pointing left or right. That's how many steps it requires like to draw a cyclic structure. But that's kind of like a very comprehensive methods when it comes to this. Again, I'm going to show you what I mean. So one thing that again, if they don't change it, is that when you have an aldose, when you have an aldose is what do you call it? Aldose is can actually have pyranose, which is a 6-atom ring. But when it comes to ketose, it can have a pyranose, which is what I just told you, which is a 6-atom ring, or furanose, or however you pronounce it, which is a 5-atom ring. So generally speaking, like when you have a aldose, they're not going to tell you to draw its pyranose, because pyranose is the only option you have. So draw it. But when it's a ketose, they generally have to tell you which one you should be drawing. Of course, when we get to it, we're going to be drawing both for practice. But again, in terms of so you're like, okay, so how do you like, what is the like, how do you draw this? So this is, first of all, it's going to be these 6-atom ones, they're going to be in chair. And this 5-atom one is going to be on something called Haworth projection. Haworth, I think that's the spelling. Projection. Yeah. Cool. Yeah. Okay, so let me show you what I mean. We're gonna do one example. I'm gonna do one example, and then you do an example, and then we keep going. So, but again, believe me, there's like always ways to make it tricky. So first of all, so let's do this example. Let's just draw the aldehyde like this. Sorry. This was going to be your example. My bad. It doesn't make a difference though, but because I try to make yours more to have like more points, so you pay more attention. So first of all, again, this is an aldose. It has an aldehyde, so I'm supposed to draw its pyranose. So what do we do first? First, we figure out, we find our aldehyde or ketone. Okay, check. 2, we number it from that side. So this would be 1, 2, 3, 4, 5, 6. That's numbering my carbons. Okay. So what's next? So 3, the 3, so the aldehyde or ketone will be turning into an amino acid. It's not a step, it's just like a fact. And it will turn into an anomeric carbon. So based on the expected length of your ring, find the OH that attacks the aldehyde. So look, I have to find out like which one of these OHs is gonna be the one that attacks it. Okay. So it's a 6-atom ring, not 6-carbon ring. And obviously the one that gets attacked is this guy. Like that was the case with all of the previous, the last chapter. That carbon double bond O is going to be attacked, whether it's a ketone or aldehyde. So we're going to be like, okay, so I have to get a 6-atom ring. So when I'm going down, the 6th atom has to be oxygen. We are like, okay, sure. 1, 2, 3, 4, 5, 6. So that's the oxygen that does the attacking. Okay. So this oxygen meaning attacks this, and this guy breaks. Again, don't worry about protonation and deprotonations. It's a tautomization. Like it's just like the protonation and deprotonations will happen. Like this oxygen will lose its hydrogen, and this oxygen will grab a hydrogen and turn into an OH. But these are the ones that are attacking. Okay, so we figured out like where the oxygens are. So then what do? We actually draw the chair. So the chair will look like this. So it's an oxygen. So this oxygen is this oxygen. See, I'm using different colors for that. Again, it lost its hydrogen. That's just something that happens. Cool. But then I said, again, technically, based on all of these examples that we've been doing, you could have actually put carbon 1 either here or here. But because if you, by convention, and again, a lot of the rules that we're talking about has to do with like where you put it. So we put this carbon number 1 clockwise to it, which would be here. So that's the carbon. Whoops. So that's the carbon. Okay. So what else do we have? So it will be carbon number 1. Yeah, so that's carbon number 1 for aldehyde. Because again, we have to number things to kind of not lose track of where things are. So, and then it will become, yeah, so then the number of the rest of the carbons, meaning that, okay, sure. So it will be 1, 2, 3, 4, 5. You're like, where's 6? We'll talk about it. So, then we're like, okay, so number the rest of the carbons. And okay, so we have to figure out like where everything's are in terms of branches. Okay, so well, technically this is us. Like I need to just put branches there, right? So based on the previous chapter, what do we say? So when you attack yourself and you create the hemiketal or hemiacetal, that your 8 chiral center, that's not a chiral center. It suddenly turns into a chiral center. It does. And what do we say when you go from achiral to chiral? You have to draw both of them. So it means, see? So this, let's say, I don't know, let's use different colors. So this O will be once for axial and once on equatorial. Like that. So now we have, okay, so now we got taken care of this. So now we're going to do the rest of them, okay? So we're like, okay, so again, remember I said everything on the right is down, everything on the left is up. So 2, the OH is down. It's on the right side, so it's down. So I'm going to draw it down. 3, the OH is on the left, so up. So up would be, in this case, equatorial. 4, the OH is on the right side, so that would be down. Okay, so on the 5, okay, you see, like, again, if you actually don't, this is where a lot of things go in a bad direction. You have to think, okay, my carbon 5 is attached to an oxygen that attacked. So that's that one. So, okay, sure, that's already taken care of. But then you're like, wait, I have a CH2OH, so CH2OH is actually a branch. CH2OH is not part of the ring because carbon 5 is attached to this and it's attached to this. But then you're like, the CH2OH is neither on a left or right for me to place it anywhere. What should I do? So this is what I was talking about in point 9. I said that if your CH2OH is supposed to be a branch and it's not either on left or right, what do we do? Again, this is already on the ring. So it's really, it doesn't have to be on the right side. We actually bring it to the down and see where the CH2OH end up at. If it is on the left side, then it's up. If it is on the right side, it's down. So we rotate it like this. The CH2OH will fall on the left, hydrogen here, OH here. So the CH2H is on the left, so left is up. So we draw it like this. That's CH2H. Make sense? Couldn't you have rotated right too, or not? Well, if I rotated right, then because again, I want to know where the hydrogen and CH2OH is, right? Because that is already on the ring. So I want to bring this to the bottom. So those CH2OH and hydrogen will be on the sides. So if I rotate it this way, well, I mean, rotate it this way, the OH will be here and the hydrogen will be down here. So that still doesn't settle the hydrogen part. So you have to, that's why you bring the OH to the bottom first, then you look at the CHOH and hydrogen. Yeah. What's up?
So I'm a bit confused about the OH on the first carbon. So how come we have an OH there? I thought the OH leaves.
I never said anything leaves. Why would it leave?
Based on like the reaction mechanism. So like the OH from the fifth carbon attacks the first carbon and then the O leaves.
Why would it leave? I'm just breaking a double bond.
Oh, that's a double bond. Okay, I see.
That's an aldehyde. Yeah.
Okay, makes sense.
Yeah, like that's literally the equivalent of this step. I'm gonna answer your question, so 1 second. So you see, like this OH is that alcohol that it's attacking, and that was the aldehyde. So this attacks, this breaks, and you do create a chiral center. See, that's the OH that was Amir was talking about. I mean, of course, it doesn't leave, but it just turns into a single bond. So this is technically what we talked about. Now we just call it a carbohydrate. But of course, you have to pick here. You only had one option for attacking. Now you have multiple options. You have to pick the right one. And again, a lot of people think, isn't it always the second last OH? No, it's not. You'll see very soon. That's not the case. Again, I'm gonna be breaking a lot of like correlational like assumptions you have in the next 1 hour. Cool. What's up?
Does the same rules apply as like, you know how the OH attack, well, the oxygen attacks, and when we numbered the carbons, it was like up to 5. Well, is it the same thing with the self-attacking where like it can only be 5 or 6 to do this? Or like could it be more? If that makes sense.
Yes. Yeah. So good point, but that's where it comes from. Yes. But again, I kind of said, so this goes back to this rule that when it's aldose, it has to be actually 6 atom ring. It can't be 5. Again, they change it sometimes. So what you're asking about is this, and yeah, that's where it comes from. Yes.
Okay, thank you.
And they have fancy names for it. Cool.